So far in dynamics, we've been talking about a lot of different types of motion. And a lot of it we've talked about in a directional sense, our like rectilinear, curvilinear, projectile motion. In our last video, we talked about absolute dependent motion. And we really saw that with pulleys more than anything, with the idea that two particles are connected and their velocities are going to depend on each other. But we're also going to talk about one other form of motion here in this kinematic section before we start moving into more of the kinetics and forces with work and energy and all that kind of stuff. It'll be the last little bit of kinematics motion thing. And that's going to be relative motion. Because a lot of times in our world, in general, systems are really complicated. And a lot of times it can be easier to describe things in relative motion, as in like something with respect to something else, rather than in absolute terms. So for example, maybe it makes more sense to talk about how fast a propeller is spinning on the front of a plane relative to the plane, rather than trying to account for the plane's motion and how it's moving with respect to that. Or maybe you've seen like a TikTok video where some guy will run a marathon on a cruise ship, and he'll show you that his cruise ship marathon, so here's the cruise ship, and as it sails through, the mapping data will look like this, right, as the boat moves through the ocean. When really it would make more sense to describe it as a relative motion, where the runner is just running in circles on the boat. But what you get in real life is this spirally thing. So the idea of relative motion is using this idea of him going in circles on the boat instead. His motion relative to the boat, rather than his absolute position in his space on Earth. So that's what we're talking about with this relative motion, that it's easier to describe things, really complicated systems, with these with this relative motion from one particle to another rather than in absolute terms. And we can choose any type of coordinate system for this. We'll see it in the XYZ a lot, but we can use any coordinate system we like. And the way that we'll see this set up is usually you'll have a fixed observer. I'll say, here I've got my little guy who is stationary. He's just a fixed point, just like we used in the pulleys. We used a fixed point or a fixed origin. That's what he's going to be. He's going to be our fixed point, and he is our origin. So here's like a X, Y, Z, kind of coming off of our origin there. And then we have another particle. Maybe we'll say, here's a guy who's running. So this guy, he's running on the path next to the lake. Right? So he's going this way, following this path along the lake. He's moving. But while he's moving, we can see here's another particle. I'm gonna draw it as a puppy dog. So here's a puppy dog, and he's running. They love to do that. He's running. Here's the path he's running along. Where I've got this puppy dog who's moving along a path. I have a man who's moving along the path. And then I have this other guy over here who's my origin. So sometimes it makes sense to describe things, describe the motion from one particle to another when that translating axis is moving. So like if I want to know the speed of the dog with respect to the running man over here, I'm going to give him like a whole separate set of axes. I'll call those X, Y, and Z prime, where now I've got my observer who's moving, I've got the man who's still stationary over here, and I have the dog who's moving. And what I can do is create a system of vectors to relate all of those things together. So my man, he can see the dog moving, right? He can see this dog moving. I'm going to call this like the position of, I'll call it D for dog. Right, so there's the position of the dog from the man. So the man is at the fixed origin. I've got the vector from the man to the dog. that is an absolute position. So in this case, RD is going to be an absolute position because it's measured from a station that's not moving, right? Absolute position, since it's measured from our man who's not moving. Likewise, from our man who's not moving to the running man, straight line vector, and I'll call this the position of A for A man. Our running man, our A man over here, who is moving, has an absolute position relative to that fixed origin. So both RD and RA are absolute positions because they're measured from a fixed origin that is not moving. This is our fixed origin. They give us absolute positions even though our man and our dog are moving. But the distance between them, right, we can make a third vector that gives us the position of the dog relative to the man. So we would call that position of the dog with respect to the man, with respect to A there. So that with respect to D/A, this is dog with respect to A. How the dog is moving from how that running man is seeing it. And so these relationships can be really helpful for these complex systems of motion, and they have some pretty simple equations. Where these equations, to relate all of these vectors, we're going to have the position of R, and I'm just going to use B and A for defaults. Position of RB is going to be the position of RA plus the position of RB with respect to A. And this order does matter, because if you flip this around and you say RA is RB plus RA with respect to B. So it matters which way you do this to get your signs correct. But this is it. This is as complicated as it's going to get. It's just vector addition. Right? It's just vector addition to find that B with respect to A, that position or velocity or acceleration of A with respect to B or B with respect to A. So likewise, you can take the derivative, just as we've talked about in all of these lessons before. Take derivative of position, you get a velocity. Take derivative of velocity, you get an acceleration. So these equations still hold true for those as well. VB is going to be VA plus VB with respect to A. Acceleration, again, still these are all vectors. Acceleration of B is going to be acceleration of A plus acceleration of B with respect to A. So we can use these relationships and all kinds of vector analysis in the scalar form using trig, or whether we use vector addition, vector analysis, as we did kind of like at the beginning of statics. Either of these we can use to solve these vector problems, to kind of relate these things together. But let's take a look at an example. In this example, we have a train traveling at a constant speed of 60 miles an hour that is crossing over a road as shown below. If the car is traveling at 45 miles an hour along the road, determine the magnitude and velocity of the train relative to the automobile. Right, so we've got this train, it's on this bridge that is over this road. Our train is traveling in the x direction, as we have this little like xy coordinate system that they gave us. And our car, as we can see on our diagram, is going at 45 miles an hour. And it's along this straight road, where this straight road meets a 45-degree angle with the train. So when we're doing these problems, they're usually just a case of vector analysis, right? So what we're going to do, because we're trying to find that velocity of train with respect to the automobile, so that's how I'm going to label it, train with respect to the automobile. I want that magnitude of the velocity of the train. What we need is that equation that we just talked about. So our velocity of the train is going to be the velocity of the car plus the velocity of the train with respect to the car. So basically, like if you were in the car driving, how fast does it look like that train is moving? Does it look like it's actually moving at 60 miles per hour relative to you? Is it moving at 60 miles an hour? That's what we're trying to find out. So let's go ahead and put these VT and VA, put those into vector form. Because we know what they are, we just need them in a vector form so we can do this vector addition to solve for V of train with respect to the automobile. So our V train is 60 miles an hour and it is totally in the X direction. So that's just going to be 60 I hat. Right? No Y component, it's completely in the X direction. My drawing's a little bit skewed, but it is completely in the X direction. We're going to look at our V for our car. So we know it's 45 miles an hour. That road is making a 45-degree angle with the train, and if the train is going perfectly in the X, that means that my triangle for this VA to find the X component and the Y component is going to have that same angle of 45 degrees. The VA is going to be 45 miles an hour times cosine of our 45 degrees, and that's in the X direction, so that's going to be I hat, plus, because we're moving in the positive Y, 45 sine 45 J hat. And that's pretty much it. We found our vectors. Now we just plug it into our equation to find that velocity of train with respect to automobile. So our VT, actually I'm just going to plug it in there. At VT 60 I hat equals 45 cosine 45 I hat plus 45 sine 45 J hat plus velocity of t with respect to a, and then I'm going to go ahead and move those over, right? Move both of these terms over to the other side. Do a subtraction so that I get the velocity of the train with respect to our automobile. Plug it into a calculator, get some numbers. I get 28.2 I hat minus 38.1 J hat. And this is great and all, but it really asked us for the magnitude of this velocity of the train with respect to the car. Again, to get a magnitude, we're going to do just like we've done before, and that's going to be the square root of our squares of the components there. So the magnitude of the velocity is going to be 28.2 squared plus 31.8 squared, which gives us a magnitude of our velocity of that train with respect to the automobile from our calculator is giving us 42.5 miles per hour. 42.5 miles per hour. So a little bit slower than this actual velocity of the train, right? Because this car is moving in the same direction. It's a little bit slower and it's a little bit at an angle, so it's not nothing. But it looks like, right, relative to the train, it is physically, that relative motion is slower than the train's actual motion. So the relative velocity train with respect to the automobile is going to be that 42.5 miles per hour. Let's take a look at another example here, where now we've got two cars on the road. And at the instance shown, cars A and B are traveling at speeds of 18 meters per second and 12 meters per second. So 18 meters per second is this little red one that's in the upper right corner. And then our B is this yellow one that's in more of like the center of the image. That's at 12 meters per second. While A has a decrease in speed of 2 meters per second squared, while B has an increase in speed of 3 meters per second squared, we want to find the velocity and acceleration of B with respect to A. Again, a lot of these, they love to be very wordy. So we've really just got to pick out all of the information that we care about. So we can see we have our velocity of A. That is going to be, and really it's a speed. This is not the vector form of it. So the speed of this, of A, is 18 meters per second. The speed of B is 12 meters per second. And we're finding velocity of B with respect to A. Right? Sounds simple enough. We've got an equation for that. And then looking at what else we need to write down, let's go ahead and pull out all those accelerations. So acceleration of A has a magnitude of -2. It's decreasing in speed, -2 meters per second squared. The acceleration of B has a magnitude of 3 meters per second squared, increasing in speed. And we want to find the acceleration of B with respect to A. So that's picking out everything important that we found. Now it's just a matter of finding those in the vector forms and solving for that B with respect to A, whichever one we happen to be doing. So I think I'm going to start with my velocity. I'll do that in yellow here. So here we're going to solve just for velocity for right now. So velocity first. Let's take a look at these vectors. So if I come over and look at my velocity vectors, I have A is moving with rectilinear motion, straight line. It's moving straight on this road at 18 meters per second. And I have an XY coordinate system where this road is at a 60-degree angle. So when I'm breaking down this velocity for A into the vector form, I'm going to get, I kind of put this in like a little triangle for perspective. I have my velocity of A going downwards on the road. So I'll notice that means my X and my Y are actually both pointing in the negative X and Y direction. AY, BAX, with this angle of the road at 60 degrees. So my vector here for this guy, my X component is going to be -18, in our negative X direction, -18 cosine 60 degrees. That's the X component. Minus, it's going to be a minus because our Y is also in the negative direction, 18 sine 60 degrees. That's our Y direction. That's our J hat. And then let's go ahead and take a look at this other car, this B car that we have over here in this brownish color. It is moving at 12 meters per second. And actually, let me use a different color. I'm going to use this blue. That sounds out a little better, I think. All right, moving at 12 meters per second. And where it is right now, it looks like this 12 meters per second is totally in the negative Y direction. Totally in the negative Y direction. So really, it's just going to be -12J. I don't have to do any more complicated math than that. Our velocity of B is just in the negative Y direction. It's also, if we'll notice, he's merging from a curvilinear. Right? He's merging from this curvilinear highway over here, but velocity is always tangent to the curve. So this velocity in this 12 meters per second is still just in the Y direction. Just in the Y direction. There's no velocity in any other directions there. It's just -12J hat. So from there, it's pretty easy to solve. It's a lot like our last problem where we're saying the VB equals VA plus VB with respect to A. So that's going to give us -12 j hat equals negative 12 cosine 60 I hat minus 18 sine 60 j hat plus velocity of b with respect to a. And so when I solve this for velocity of b with respect to a, I'm going to get velocity b with respect to a 9 I hat plus 3.59 j hat. And this did ask for, oh, it just said velocity and acceleration, but it's going to make more sense to put it into a magnitude, so we'll put it into a magnitude anyways, which is just the square root of the squares. Alright, this is a vector form, now we're looking for the magnitude. 3.59 squared plus 9 squared is going to give us a velocity for b with respect to a magnitude of velocity, also known as a speed, 9.69 meters per second. For our velocity of the little brown car here, the little yellowish brown car, how it's moving with respect to the little red car. For its speed, for its velocity there. Fairly straightforward, like our last problem. But we also need to do the same for acceleration. So let's go ahead and break down the acceleration. And I'm going to just delete all this velocity stuff. If you really want to see it again, you know how to rewind a video. I don't have to tell you. Let's do the acceleration. And maybe we'll do it in pink. Alright, so let's find our acceleration vectors. We know the magnitudes for the acceleration for our two cars. We know that this guy going -2 meters per second. He's slowing down in order to be very nice and let our little yellow car onto the highway. So he's decelerating. But bear in mind, in our coordinate system, that deceleration of 2 meters per second is actually in our positive x and y. There's our 60, here's ay, here's ax, which means that our a of car A, that vector acceleration, if we break it down, is going to give us 2 cosine 60 I hat plus 2 sine 60 j hat, where those signs are just coming from where we're oriented in the coordinate system. So let's take a look at our yellow car again. Right, 3 meters per second, and that is in the negative y direction as well. But very important that we note that 3 meters per second that's going just in the y direction is not just the y direction, right? This car is coming off of a curve. It's going through curvilinear motion, where actually this 3 meters per second squared that was given to us, that's actually going to be our acceleration in the tangential direction, right? It's going around that curve. So this 3 meters per second is actually our AB in the y direction. Right, our tangential acceleration, tangential and normal accelerations, as we did for curvilinear motion. We have a radius of curvature, we can find what that normal acceleration is, right? To find what our acceleration for B in the x direction is. So our acceleration is going to be for B. We're looking for that y component, or sorry, we have that y component, we're looking for that x component. That y component we already know, -3 j hat. The x component we can get from an is v squared over rho, right? Velocity squared over radius of curvature. We know that velocity squared is, or we know what the velocity is, I should say. We know what the velocity is, we know what that radius of curvature is. They're both given to us, so we have that 12 meters per second squared, all over radius of curvature, 100, and that's going to give us 1.44 meters per second. And remember, that's moving in towards the center of the circle, so that's going to be a negative 1.44 I hat for our acceleration of b. So now that we've got that, now that we've remembered all that, just a matter of doing that vector addition. Let's go ahead and pop those into our equation. Our equation, of course, is going to be acceleration of b equals acceleration of a. Pretend that's an arrow. Oof, that is so rough. Okay, we're just pretending that's an arrow. Acceleration of b with respect to a, and that's an arrow too. All right, so we're going to pop all of those guys in there. That's going to give us negative 1.44 I hat minus 3 j hat equals 2 cosine 60 I hat plus 2 sine 60 j hat plus acceleration of b with respect to a. So I'm going to type those into my calculator, adding the i's together, adding the j's together. Typing that in, I get acceleration of b with respect to a, negative 2.44, not cosine, negative 2.44, just negative 2.44 I hat, minus 4.732 j hat. So that's going to give me, that's my acceleration, sorry, that's my acceleration vector. We're going to find the magnitude, take the square root of the squares. I have a bad habit of dropping negative signs when I do this, but it's just because I know it's getting squared. Everything is going to be positive under this square root. So that when I get a magnitude, pop that in the calculator, it gives me 5.32 meters per second squared for my acceleration of that little the little yellow car up here with respect to the little red car. So since the red car is slowing down and b is speeding up, it really looks like the yellow car is accelerating much more than it is, right? That relative motion of b with respect to a, significantly more, significantly higher acceleration for this relative motion scenario. Alright, I've got one last problem for us today, and I really want you to go ahead and try this one on your own before we talk about it and walk through it together. So this is going to kind of combine what we did in the last lesson with the pulleys and absolute motion with this new concept of relative motion that we've been talking about in this video. So here we've got a motor draws in a cable at C, so that's C is over there on the right side, with a constant velocity of 4 meters per second. The motor in the cable at D, and that's the other side, that's our lower left corner, draws in the cable at D with a constant acceleration of 8 meters per second squared. If Vd equals 0 at time 0, determine A, the time needed for block A to rise 3 meters, and B, the relative velocity of block A with respect to block B when this occurs. So go ahead, pause the video, give this a try, and it's kind of combining some of these skills that we've worked on so far. Go ahead, give it a try, and then we'll talk through it together. Alright, let's go ahead and take a look at this system. So if we're going to go ahead and look at part A, that's what we'll do first. We'll go ahead and do part A here. We want to find the time needed for the block A to rise 3 meters. And if we look at this set of systems that we have over here, we're going to see that if we're looking at block A, there's really only one cable, right? We don't actually have to account for anything that's going on with B and C. We only need to account for this AD system to find the time needed for block A to rise 3 meters. So what we're going to do is we're going to establish our datum, right? We've kind of looked at how this thing is moving. This point D is moving downwards. Then we're going to have A moving upwards. And so we want to establish a datum here. Right, so a good one to use for us might be going through D. And we've got a fixed point at the center of D. We can make this a datum where we have the velocity of D coming downwards. Okay, so VD, they give that to us. Motor draws in the cable at D with constant acceleration. Oh, they didn't give us VD. They actually gave us AD. AD is 8 meters per second squared. But what we're going to do first is set up all of those length relationships. Okay, we're going to set up our length relationships so that we get our length from the datum to D, one length of rope that we have, and then we're going to have 2 lengths from the datum to A. That's going to be our total length is SD plus SA plus SA. So this relationship that we get when we take the derivative is going to be BD negative 2 BA. And we can get the relationship for that acceleration as well. It's same deal. Acceleration, if I take a derivative, is negative 2 times the acceleration of A. So I can work backwards. I can work out to my acceleration, which I know, it's 8 meters per second. And then I can work back to my velocity because I'm trying to find this time needed for block A to rise 3 meters. And I know that if I want something related with a time and a position, that velocity is usually a really good way to do that, right? Because I can do velocity is ds over dt. The velocity is ds over dt. I want to find my acceleration so then I can back out and get a velocity, and then I can back out again. Backing out, I mean integrate. We can integrate to get out of that, to go into our position to find the time, right? That's what we're interested in. We're interested in that time. So I know the acceleration of d is 8 meters per second squared, and that's in our positive direction, right? AD is going downward, it's going into our little motor down here. That's a positive 8 meters per second squared equals negative 2 acceleration of A. So if I math that out correctly, then I'm pretty sure that acceleration of A is going to be 4 meters per second squared. Now what I'm going to do is I'm going to get back to my velocity. Right? So if I integrate acceleration with respect to time, then I'm going to get a velocity. So my velocity of A, if I integrate this with respect to time, it's just going to be 4t. Right? I integrated a constant acceleration, so my velocity is 4t. And I can integrate again to get a position. If I integrate this again, I can get the position of A equals negative 2t squared, where this is dt. Where now I can find that lift, right? I went from a position of 0 to a position of 3, right? So I'm lifting, I'm going in the opposite direction of my coordinate system. I'm lifting. And if it helps, maybe it's easier to think about this as like definite integrals, where the integral from 0 to the position of negative 3, again, because we're lifting. Because we're lifting, it's going to negative 3 of this velocity. right? This velocity term, this is really like ds. If I put it in these terms where we had VA equals negative 4t, you can think about it like this, where we plug in negative 4t equals ds dt. And so ds equals negative 4t dt. Right, this is what I'm doing over here when I'm taking this integral and getting position of a equals negative 2t squared. But sometimes it helps to write it out like this. You can visualize it a little bit better. And then I'm going to integrate. I don't know what my time is. I know I start at time 0. It did tell me that. Right? VD is 0 at time 0. So that's how I got these lower limits for integration. And I started at position 0. And then I'm going to time t, because that's what I'm looking for. I don't know what time is. So here I end up with negative 3 equals negative 2t squared. Right, so negative 3 we could have input over here. This is the lift at the time we're looking for, that lift of 3 feet. So either way, we get there either way. Solve for t. Right, so I solve for t, and this is going to give me 1.22 seconds. 1.22 seconds to lift block A 3 feet. So that was our part A. And then our part B, our more recent stuff. That was really all like 12.9, the absolute motion of two particles that are attached to each other. Now part B is asking for the relative velocity of block A with respect to block B when this occurs. Relative velocity of A with respect to B when this occurs. So we know we've got an equation for this. Velocity not of B, you have to start with the letter that you start with, right? So we're starting with A, so this starts with A. Velocity of A equals velocity of B plus velocity of B with respect to A. So we know what we're looking for. Do we know our velocity with respect to A? We do, right? We have a relationship for that. We said VA is negative 4t. We already solved for that in this part A. So VA is negative 4t. We also found the time. We've got a time that we can plug in there to find that velocity. So in this case, velocity of A is going to be negative 4 times 1.22. That's negative 4 times t. Gives me a velocity of negative 4.88 meters per second. That's going to be our VA. So now we've got this guy. The only guy that we need in order to find for our last guy is VB. And he's a part of a whole separate system. So we're going to need to go ahead and find what that velocity of B is in order to find what our relative velocity is. And if you do a couple of these pulley problems, it might feel a little bit intuitive to you. Because in this, we have our, at C, the motor at C is pulling in with a velocity, a constant velocity of 4 meters per second. So you might be able to figure out, okay, if I have this guy pulling in at 4 meters per second, and I've seen a lot of these pulley problems where I have one side and then another side, so I have like 2 lengths of B, that my velocity of B is just going to be half of the velocity at C. And you'd be correct, right? VB is going to be half of that. There's 2 ropes that are sharing this like 4 meter per second velocity. VB is in fact 2 meters per second, right? And it's technically a negative 2. But if you don't see that, it's okay. You haven't worked a lot of pulley problems. That's perfectly fine. We can go through the exact same process that we went through on the first one, where we say, okay, I've got just this one single section of rope here, and I have C coming in. I've got this fixed point at C. I'm going to give myself a datum there. Through C. I don't have to use the same datum. This is a separate system, right? This has its own thing going on. I can make my own relationships for C and B. And it doesn't really matter because they're absolute anyways, right? They're absolute anyways. So if I make my datum there at C, what I'm going to see is I have this position of C, and then I have 2 positions of rope down to B. If I'm finding that overall length of rope equation for this, I'm going to get SB plus SB minus SC, right? I have this little section of SC here that is getting subtracted out where C is going in at that velocity. Just like we've seen in some of the other problems. When I take a derivative here, I get 0 is 2VB minus BC. Goodness, making so many errors in my writing today. Getting sleepy. So what I'm going to end up with is 2VB equals VC. Now notice that our VC is going the opposite way. Our VC is going up 4 meters per second, pulling that in, which means that 4 meters per second is actually a negative 4 meters per second. So 2VB equals negative 2 meters per second. VB, oh my gosh, I can't get my mind right. Jeez, I gotta end this video soon. We're almost done. We're almost there. It's 4. It was given as 4 meters per second, right? Yep, here it is. Getting ahead of myself. VC is 4 meters per second squared. That equals 2VB, so when I divide the 2 over, now I get to what I was thinking. VB is negative 2 meters per second. Oh, okay, almost there. Last thing is to just plug it into this equation here. And we're going to plug into this guy. VA equals VB. VA equals VB plus VB with respect to A. So plugging into these guys, notice I'm not actually taking into account like my I hat, J hat here because everything is moving in one direction. You're either up or you're down, right? Everything is in the Y direction. So our positive and negatives indicate that for us already. I don't actually have to do the I hat, J hat coordinate system. So negative 4.88 equals negative 2 plus VB with respect to A. This is going to give us our velocity of B with respect to A is 2.88 meters per second. So velocity of B with respect to A. So you happen to be riding the elevator here at A, and you look up over at B. The speed of B relative to A is going to be 2.88 meters per second.